Okay, so now at least for me the time is 5 o'clock, so I guess we resume now. So we will be hearing from Peter Rindau from Basic Research in a joint paper with Daniel Masny. And we'll hear about endemic oblivious transfer. I was considering making a silly joke about pandemic oblivious transfer, but I thought that was such a bad joke that I'm definitely not going to say anything about this. So I'll just hand this over to you, Peter, immediately.
Yes, maybe I'll start with the why we called it endemic, which in Greek, I guess, originates from like native. And so endemic was our, the security notion that we'll introduce, we think is sort of native to all oblivious transfers, sort of more fundamental definition. And so that's what endemic means. Also sometimes used for diseases. Yes. Anyways, so what is oblivious transfer? Well, probably most of all of us know, but the basic version, we have a sender and a receiver, and the sender has two messages, two strings, M0 and M1, and the receiver has a bit, C. And when they run the protocol, the sort of output is that the receiver should learn the message MC. And they should not learn anything about the other message. And moreover, the sender should not learn which message the receiver received. And in this talk, we asked the question of how can we construct versatile, highly efficient, and fully secure oblivious transfer, which are sort of tailored for the random oracle model. Along this line of work, we introduced a new protocol, and it's flexible in that you can base it on many different assumptions. So examples are like DDH, CDH, and interestingly, we sort of easily get post-quantum secure using a LWE based construction. And all these are in the same framework and sort of modularly designed. Along the way, we sort of an artifact of how our protocol ended up working is that we started thinking about how to model security, and we came up with a new security notion that we call endemic oblivious transfer. And using this different definition of what it means for oblivious transfer, we are actually able to achieve a one-round oblivious transfer protocol, while previous results had shown that you need at least 2 rounds of interaction to do an oblivious transfer. And we do this by weakening the requirements on the oblivious transfer itself. And so this old impossibility result still exists, but we sort of circumvent it. And then in the last bit of the talk, I will go over oblivious transfer extension, how we can use our security definition there. And along the way, we found several sort of attacks and in addition fixes that sort of allow us to do different things in the oblivious transfer extension setting. So yeah, everyone here probably knows and loves oblivious transfer because it is complete in that giving an oblivious transfer functionality, Killian and 88 showed that you can compute any function you want. And this has been used to great effect by this community. Yeah, there's obviously the classic garbled circuit protocol and many, many other ways to use oblivious transfer to construct larger primitives that we're actually interested in. So given, first I'll go over, I'm sure most of us know, but sort of go over what it means for something to be secure. So in the ideal setting, we have this functionality, which as I described earlier, but in the real world, right, we're going to be running a protocol where we're sending messages back and forth. And for our protocol to be secure, we'd like to say there's equivalence between these two interactions. One where it's, I use this diamond notation to denote sort of idealized functionality and the protocol below. And so we'd like to define an equivalence between these two in order to claim security. And the classic way you do this is, it's a simulation-based paradigm where for every adversary in the real world, we're sending real protocol messages, there exists sort of a new adversary prime, which consists of the old adversary and the simulator. And the job of this simulator is sort of twofold. First, it needs to, hence its name, simulate the messages that the honest receiver would be sending. So the messages in the top should be indistinguishable from the messages in the bottom. And this is sort of one of the basic requirements. But in order to claim security, we need to say that we need to sort of what's called extract the effective inputs of the adversary. And in this case, since it's a malicious sender, they have two OT messages, M0 and M1. And so the simulator needs to somehow figure out what these messages would be, and then forward these on behalf of the adversary to the ideal functionality. And since if such a simulator exists, then it's sort of, we can argue security because the adversary can't tell whether it's in the real world or this ideal world where it's secure by default. And so critically, we need to do this extraction step. And similarly, when we consider a malicious receiver, instead of extracting the two messages, we now need to extract what their choice bit C is, and then forward this to the ideal OT functionality, and we get back the message MC, and then the simulator has to forward that back to the adversary in some way, without the adversary being able to tell that this is happening. So this is sort of what it means for something to be secure in the simulation-based paradigm. And now let's sort of start looking at how you might construct an oblivious transfer. So this first one is sort of this sort of very naive, semi-honest protocol based on DDH, and it ends up being incredibly simple. First, the receiver will sample a private key, little a, and then they'll compute the public key, big A, subscript C, the choice bit, which is G to the power A. And then they'll pick the other, so the big A is the public keys, and then they'll pick their other public key as just uniformly at random from the space of public keys. And then they'll simply send over these two public keys in sort of a fixed order. And the sender will run the other half of the DDH protocol, where they sample a private key, the public key, G to the B. And then they do the DDH operation where they raise the other public keys, the A's, big A's, to the power B. And this allows them to come up with two common keys, or two keys, K0 and K1. And they'll encrypt their messages under these two keys, K0 and K1, along with sending their public key B back. And now the receiver can similarly use the public key B, raise to the power their secret key A to compute the common key K subscript C, and then decrypt the corresponding message. And this just follows from like the sort of commutative property of DDH type assumptions. So for the rest of this talk, I'm sort of just going to hide the encryptions that I'm sending. And so instead of writing out the encryptions, I'm just going to say E0 and E1, and these are sort of encryptions under the corresponding keys of the messages. And now we can ask, so this protocol ends up working, but it's sort of naively insecure against a malicious receiver. And in particular, we require the malicious receiver to simply pick the public key that doesn't correspond to their choice bit uniformly at random. And instead, a malicious receiver could simply choose the other public key so that they know the discrete log of it. And this distribution is identical, so there's no way we can tell the difference. And now they're able to decrypt both, or compute both keys, and then therefore decrypt both messages. And so pretty much most at least of these oblivious transfer protocols based on this sort of framework try to come up with some way to make sure that the adversary the malicious receiver cannot do this. Can I come up with the second public key that corresponds to their private key? Bellare and Micali way back, figured out a way to do this. And what they first do is they send over a random public key R, just picked uniformly at random. And then we require that the receiver to have the constraint that their two public keys are off by this fixed value R. And this way they can pick one of the public keys, but then they can't choose the other one. That's sort of the intuition here. Because they're off by a fixed amount. And then the receiver can just send over the first A0, and the sender can then reconstruct the other A1. And then the rest of the protocol continues as the same, using the DDH type assumption. And this is great. You know, this ends up working, and it has been widely implemented. One drawback of this is when you start looking at what does the proof look like for this for a malicious receiver. Well, the simulator is quite simple. First, they pick the random R as before, and then they let the adversary do what it wants. It gets back A, and then it can compute the other A1. And now the simulator's task is to figure out what the choice bit C is. But we have a problem here in that sort of information theoretically, the message A0 contains no information about what their choice C is, right? Both A's are sort of uniformly distributed, subject to being off by the fixed amount R. And so there's no way to figure out whether the receiver's choice bit is 0 or 1. And this ends up being a problem in that now our simulation-based security paradigm does not work for this protocol. That is not necessarily to say that this protocol is, quote, like broken. It's just to say that we can't prove that it's secure in the simulation-based paradigm. Some have noticed that later on, the malicious receiver actually has to run this the value that they want through the random oracle, and this allows you to, at some later point, figure out what the choice bit is, but it's sort of already too late. And you can work around this. In fact, like Jack, who we saw earlier, added some workarounds to make this work, but it ends up adding additional overhead and additional rounds of communication in order to make this simulation-based secure. And then more recently, Chow and Orlandi had optimized this protocol using a slightly different variant of sort of cleverly reusing messages, but it still suffers from the same basic attack, but only that now this R value is now B. And so we still end up having the same basic issue. And in fact, this Chow-Orlandi protocol is one that's most widely implemented and used in most implementations out there. And it's sort of curious that they typically claim that the larger protocol is simulation-based secure, but almost all implementations that use this are not, because it can't extract the choice bits. So this is sort of a technical, I might be being picky here, but we'd like to have a fully secure, highly efficient oblivious transfer protocol that sort of fits into the simulation-based paradigm. So there do exist such protocols. So for instance, this one based on unique blind signature protocol, and it works, but it's ends up being very inefficient in terms of practice, especially compared to like the previous protocols, which just require a few DDH exponentiations. And so we can either achieve full security or we can achieve efficiency, but we had to choose. And so this sort of is where we come in. We ask, how do we construct highly versatile and efficient, fully secure oblivious transfers? And in particular, we're going to be interested in using the random oracle model as a way to achieve high efficiency. And so this is where I get to explaining our construction. So it begins the same exact way as before. The receiver picks their private key, little a, and the corresponding public key, big A of C, as G to the little a. And then we do something curious in that we pick these we pick first RC naught uniformly at random from the space of public keys. And then we compute RC as this formula shown here, which is the actual public key that we want divided by the random oracle hash of this other R value, RC naught. And then what we're going to do is send over these R values instead of actually sending over the A's themselves. And the sender can easily reconstruct the two A values, A0 and A1. And AC, whichever one that is simply the value that the receiver picked. But the other A value it looks like this. It's RC naught times the random oracle hash of RC. And RC naught was picked first, sort of by definition, before you can define RC. And so this effectively allows the the random oracle to control what the other public key is, and it's outside of the control of the adversary. You could say maybe, oh, well, what if they modify the value of RC, not the coefficient on this? But then that would sort of change all the other random oracle values too, because it appears both on the outside of the random oracle call and on the very inside of it. And so this is the core technique that we use to allow the receiver to pick one of the public keys, but not the other. And while we're using it here in this way, I think this is also sort of a powerful technique in general, in that it doesn't have to be used as public keys. If you ever want the adversary to be able to pick one out of some values, you could use a similar construction, and we'll see sort of generalizations of this. But yeah, so I just want to note that you might be able to use this trick in other places. And in fact, I've heard of such rumors. Anyways, moving on. We effectively can say that the receiver can choose at most one of these public keys. And then we simply finish the protocol as before. We compute the common keys using DDH, and then we can send over the public key and the encryptions of the messages. And now what does our simulation look like? Well, in the case of a malicious sender, it's pretty easy. The simulator basically just runs the protocol of the honest receiver, except for it does some extra random oracle trickery, which allows itself to know both of the public keys and their corresponding private keys using the power of the programmable random oracle. And this allows the simulator to decrypt both of them and then forward the messages to the ideal functionality. Sort of the more interesting case was against the malicious receiver and needing to extract the choice bit C. And the way this works is we run the receiver until we get the first two R values. And then we look at the order in which these R values were queried to the random oracle. And we can figure out that the R value, RC naught, that was queried first, sort of defines what the C value is. And so we can first figure out, we can just look at when these R values were queried to the random oracle, and then define RC naught and similarly R or C. And then just simply forward this C value to the ideal functionality. And you can formally show that they have to query this first RC naught before RC. And then we can simply complete the protocol as before. So that's sort of the intuition. And then additionally, we have to program in the DDH challenge, but I'll omit that for now. So up to this point, I described the protocol in terms of DDH, but we actually don't use any sort of special DDH assumptions. In fact, we show that you can construct this oblivious transfer from just about any key exchange protocol. So shown here on the left is a sort of a standard key exchange flow. And then shown here on the right is how we modify this protocol to achieve an oblivious transfer. So you can see that first, both in the key exchange and in the OT protocol, we run the KA algorithm with a random tape little a. This gives you a public key, big A. And then in the oblivious transfer world, we use the random oracle to define this other R value. And then we can send the R values over and we run the second phase of the key exchange, KB, as shown here. And then we finally do the key, the sort of computation of the common key, and finally here at the end. And so given that this protocol is sort of very modular and can build on just about any key exchange protocol, we're able to effectively get an oblivious transfer from a wide range of assumptions. So our requirements on this key, we do have, not any key exchange protocol would work. We have some requirements on it. And first is that the key exchange protocol must have the public key space must form a group, because we need to be able to do this group O- and O+ on it, on public key elements. Second requirement is that we need a random oracle, which maps an arbitrary bit string to a public key. And moreover, you shouldn't be able to distinguish a uniformly random group element from an actual public key. And so these two distributions need to be the same. And so long as your key exchange protocol satisfies these requirements, then you can instantly plug it into our framework. And as a result, we can instantiate our oblivious transfer from, say, the DDH assumption, which I showed you earlier, or the CDH, or even LPN-like assumptions, which means that we achieve post-quantum security if you instantiate it with LPN. And we'll actually see some performance numbers later on. That the LPN-based construction is actually, funny enough, the fastest, although it uses more communication. And I think that's, yeah. So this is our main construction shown here. Next, I'll talk about how you can actually generalize this to several other types of oblivious transfer. So first I showed 1 out of 2. However, you can easily get 1 out of n oblivious transfer. The main observation is that you first make the receiver choose many R values, every R value except for RC. And then you define RC with respect to all the other R values. So it's shown here on the left is sort of the formula, how you define RC as a function of all the other R values. And this sort of effectively ties the hands of the receiver so that they only can choose one public key. And this is sort of one of the things that I was referring to, that you can maybe use this in other places and that you can get 1 out of n. And in addition, you can also sort of curiously get n-1 out of n oblivious transfer by using a different way of linking the R values, by defining the next R value as a function of the previous one. And this effectively means that the adversary first has to pick one R value and then it can choose all the other ones sort of adaptively. And you can actually do sort of k out of n using this random oracle trick. But we don't present it in the paper because it actually requires, when you combine it with this oblivious transfer, you end up needing stronger assumptions and you can't just get it from DDH. So we just showed these two, but you can sort of do tricks to get k out of n using this random oracle trick. And it's sort of just, yeah, all you need is the random oracle in sort of a group. Yeah, and so that's sort of ends when I'm talking, my discussion of the classic notion of oblivious transfer. But almost everywhere in practice, we don't need to use this functionality where the sender can choose the messages. And instead, we often use a variant of oblivious transfer where these messages, M0 and M1, are just simply uniformly random strings because we just use them as keys. We don't really care what their value is so long as they're random. So the examples of this is like garbled circuits, where we have random wire labels, private set intersection, and many other like speeds and so forth. And so it's actually okay, instead of having the sender choose these messages, to simply allow the functionality to output the sender's messages, M0 and M1, so long as they're sort of quote unquote random. And this is what's often referred to as random oblivious transfer and is used in practice. So we were thinking, oh, maybe we can get efficiency gains by, as other protocols do, by getting rid of the messages and removing these encryptions and simply now defining the output messages as the sort of agreed upon key exchange values. And this is sort of common practice to do. This wasn't necessarily our idea, but we did want to show that, running our protocol like this, we can in fact show that these M0 and M1 values are uniformly random, chosen by the protocol. And then the second observation is, once you do this, is that the two messages that you send in the protocol are actually independent. Like first, at least in the DDH case, first you can, in the first round, you can send both messages and achieve one round of an oblivious transfer. But this should start to look maybe a little curious, because as I mentioned earlier, is that there's sort of impossibility result that you can get oblivious transfer, the classic notion of oblivious transfer in one round like this. And yet we're claiming that we can. And there ends up being a problem. So we can assume that whichever party is corrupt is what's known as rushing, and that they always first receive the messages sent by the other parties before sending theirs. And so if the sender is corrupt, then our protocol basically looks like this, where it's back to the original. And now what the sender could do, they could choose many different secret keys, n of them shown here. And then they could simply repeatedly try computing different values, different messages, until they find some messages that hash to a value which they like. So maybe there could be some predicate, or for example, maybe the sender always wants the least significant bit of M0 to be 1. And so they could easily do this. And so clearly these messages are not uniform, right? They have some bias in them that the adversary can control. And so we definitely don't get a uniform. And so instead, what we're going to do is define this notion as endemic OT, where the corrupt party can sort of influence the messages. Similarly, if we still focus on our one-round protocol, if the receiver is corrupt, they can be rushing, and then they can similarly first receive the B message from the sender. And now they too can choose different private keys, little a1 to little an, and repeatedly compute their chosen message MC until they find one that similarly satisfies some predicate that they choose. So each MC individually is sort of random because they output the random oracle, but they can sort of repeatedly sample from this random distribution until they get something that they like. And so depending on who's corrupt, they can influence the messages that they receive, is the basic takeaway. And one option would be to give up on this idea of having one round oblivious transfer. The other option is to simply redefine the functionality so that such attacks are allowed. And that's sort of exactly what we do when we define endemic oblivious transfer. In that whoever is corrupt is able to choose their output message. So if the sender is corrupt, they choose both messages, and the receiver is corrupt, they choose theirs. And even though the functionality allows the sender and the receiver to explicitly choose their messages, in practice, whoever's corrupt actually only has some influence, some bias on these messages. But that's sort of a technical detail, and we just model it as allowing that party to completely choose the message itself. And then you could ask, well, this is sort of a weird functionality, now allows the adversary more power. Is this useful? Can we actually safely use this new primitive in our favorite protocols? And we looked at many different applications and sort of conclude that yes, you can actually use this. And one application that we'll go into detail is oblivious transfer extension, and it sort of naturally works there with some caveats. And yeah, so shown here, I sort of discuss how the simulation works, but the main takeaway is that now we simply allow the corrupt party to choose their messages. And so the simulator can simply extract the messages that they choose, even if they are biased messages, and forward these to the endemic OT functionality in both ways. And similarly, on this other side, the receiver can bias the message that they want to receive. The simulator simply figures out what message they chose and forwards this to the endemic functionality, and everything ends up working out. And at this point, we were very happy. You know, we came up with this great new security definition, endemic oblivious transfer. We sort of showed that we could achieve UC security in one round, and furthermore from standard assumptions, along with the random oracle. And so we patted ourselves on the back, posted it on ePrint, and went home. And then, a little while later, we get what we all fear: a very kindly worded email from Jonathan Katz asking uncomfortable questions about our security proof. And at first we refuted that it is in fact secure, but after a while we realized we might have made a little omission. And it's not too big of a deal, if you ask me. But what's the problem? Well, so extraction and all this works out fine. But to show security, we need to prove that the message that the receiver shouldn't learn is sort of unobtainable to them. And the way you do this is, say, in this case, I'm using DDH as an example. The simulator is given a DDH triple, where you have sort of big A, big B, and big C, which are G to the alpha, G to the beta, and G to the alpha times beta. So this is a classic DDH triple. And what we need to do is somehow arrange so that the message that we're outputting, which the receiver should not learn, is actually the DDH triple, the C value from the DDH triple. And so in this way, we can sort of reduce the security of the receiver picking or finding the other message to breaking the DDH assumption. So this is a classic step. And the way you do this, it's not too hard. And you program the random oracle at RC such that it equals the DDH challenge A. You make it so that this is true, at least. And this was fine. We talked about this in the proof. But the way we did it is as follows. So the problem is that as soon as you send over the big B, the receiver could query this point, and then you can't program it after that. So what you first need to do is, before you even send the first message of the protocol, you need to first figure out when the adversary would query the random oracle at this point, and then you need to preemptively program it. But the problem is that at the beginning, we don't know when the adversary will query RC. And so what we end up doing is simply guessing. It's like the ith query that they make, it will be the random oracle query that we need to program, and then we'll do it. And that works great unless you want universally composable protocols, in that this guess only succeeds with polynomial probability. And so we'd have to rewind the adversary many times, and rewinding ends up not being friendly in the UC model. And so we end up having an issue here in that we rely on rewinding of the adversary. So in the update of the paper, we changed this claim from being solved to being an open problem, in that how can you get UC security without rewinding, as I showed here, and with all these other requirements. In the paper, in the standard proof that we had, we showed it sort of in the standalone model where we're allowed to rewind the adversary. We also show that if you allow for 2 rounds of communication, you can get the endemic OT functionality in the UC framework. Alternatively, and sort of my favorite, is to just come up with a new assumption. Why not? And it ends up being, in my opinion, not too bad of an assumption. It's a DDH type of assumption where we add some additional requirements. Daniel, my co-author, he's a little bit more strict and called it a strong assumption in the paper. So it depends on your philosophic perspective on assumptions, but you can also do it if you just sort of add a little bit additional requirements to the DDH type assumptions. But yeah, regardless, it remains an open problem about how you can get sort of UC secure one round endemic OT from standard assumptions. And I have an intuition that it probably would work, could happen, but I don't know how. And then the next part I'd like to talk about is, I sort of mentioned, like, yeah, is endemic OT a good security definition? Well, shown here is several relationships between how you can use endemic OT in different scenarios. And so endemic OT security notion is here at the bottom, but you can easily construct different notions of oblivious transfer from an endemic OT. So the classic notion is on the left, which is where the sender is allowed to choose the messages, and you can sort of easily get there. Similarly, you can allow the receiver to choose their choice message fully, and then combined with a coin tossing protocol, you can get uniform messages as we often desire. And interestingly, if you want uniform OT messages, this sort of implies coin tossing, and therefore the classic 2-round requirement for coin tossing would also be a requirement. And this, you can see how by removing the requirement that these messages are actually uniform, in the fact that you can get coin tossing from an OT protocol, we can reduce the round complexity for endemic security. So shown here briefly is how you might construct, say, if you want a truly uniform random oblivious transfer, how could you get it from a endemic OT oblivious transfer? Well, first we run the functionality for endemic OT at the top, and we output some messages, these M prime ones. And then we can run a coin tossing protocol, or maybe even in parallel, and then re-randomize these messages. And this effectively allows us to get a classic uniform random oblivious transfer. And you can do this in 2 rounds, as we show in the paper. Similarly, if you just want the classic notion of sender chosen message, you don't really need to do anything. You can just simply take the endemic OT, which outputs random strings, and then use them as one-time pads. And even though the receiver can bias one of the messages, this is the message that they're going to decrypt anyway, so it doesn't end up mattering. And the other M value is uniformly random by the functionality. So you end up being very versatile. If you want sender chosen, you can simply use this. And similarly, receiver chosen messages, which is sort of odd, but we include it. So at this point, I'll show you some performance value metrics and from different types of assumptions. So I mentioned earlier that this Chow, Orlandi, and Bellare-Micali work. They require sort of a stronger assumption known as gap DDH and the random oracle. And even though they use a stronger assumption, their protocol still does not allow extraction of the choice bit. And in fact, their protocols require 2 or 3 rounds of interaction. The Chow-Orlandi implementation, though, is highly efficient and it only requires 18 milliseconds in the LAN setting. But you can see that our constructions are from sort of standard assumptions, such as DDH and the random oracle. And if we allow rewinding, so the sort of standalone security notion, then we can achieve 1 round of communication. And as you can see, when we're in the LAN network, this ends up paying dividends in that we can get much better latency. But if you use standard assumptions, then we require, and no rewinding, then we require 2 rounds of communication. But another interesting property is the flexibility of our framework in that we can base this on an LWE type assumption. And so we took the CRISPR-Kyber key exchange protocol, and that's sort of in the NIST competition. We had to modify it slightly because their public key space was not actually uniform. But if you remove one of their optimizations, which is not too big of a deal, you end up getting meeting our requirements on the key exchange, and therefore we can get a 2-round, highly efficient oblivious transfer, which is plausibly post-quantum secure. And for example, this LWE-based CRISPR-Kyber protocol is faster than the DDH, which at 24 milliseconds. But it does send, like orders of magnitude more bytes of communication, just because of the type of lattice assumption. But yeah, so post-quantum OT is here. That's one of the main takeaways. Then at this point, I'm gonna sort of switch gears a little bit and talk. You can kind of view this as an application of oblivious transfer, or you can, or of an endemic oblivious transfer, or you can view it as we want to use the endemic notion to show that oblivious transfer extension can achieve the endemic security notion at more efficiency. So first, what I'm going to do is sort of give you a high-level description of how oblivious transfer extension works. So the first thing that and this is the sort of classic protocol. First thing, the receiver will be on the left, and they'll act as OT, base OT, will run 128, say, base OTs is what we call them, and the party on the left will choose the random, or choose random messages and input them to the protocol, while the party on the right will choose random choice bits, 128 of them, and they'll pick up sort of just a random set of these so-called base OTs, illustrated here. And then what they can do is they sort of can somehow, they run some way to expand these constant number of base OTs into polynomial many new oblivious transfers. So the receiver can expand their sort of these top messages into choice messages where they now act as the receiver. So the roles have switched. But crucially is that now we have many, maybe millions of oblivious transfers when we started out with 100 at the top. And then this produces two things. It produces the OTs, random OTs on the left, along with this matrix M, which you can send over to the other party. And this together, using these two values, they can construct the two sender messages. And I'm not going to get into exactly how you compute these, but basically it suffices to say is that the receiver on the left chooses their ith message with some choice, CI, as you can think of it as sort of a weird PRF, where the base OT 0 messages are the keys, and the PRF input is the index I. And this defines their chosen message. And then somehow the sender on the right can compute the two messages that they get where they're correlated by this delta term, which is just random. And so they get this known as correlated OT. And then typically if you want random OT, then you simply apply a random oracle hash to these correlated strings, and you get sort of the classic random OT. But as we just saw earlier, there's a lot of things that you can do, and these messages actually might not be truly random, and in fact, they can be biased, as we'll see here. But one thing when we started looking at this, what we want to do is use our endemic OT protocol in this OT extension. And I'll sort of talk about what we find. Interestingly, when you allow endemic OT, what this means is that the corrupt party can sort of bias the messages. And so what they end up being able to do is bias the key to the PRF, which effectively you lose sort of all security guarantees on the PRF. Then, and in fact, the PRF, this weird PRF has this form, it doesn't really matter. But the main takeaway is that if you adversarially choose the base OTs, then you're able to influence the values of the OT extension messages. And one possible bias you could do is you could make the receiver here, could make the first two OT extension OTs that come out of it, the extension, actually equal to each other. And you can then construct sort of weird protocols where this completely violates security. Because this is not something you typically expect from a random OT. And in general, you can do all sorts of weird biasing. And so traditionally, several works had sort of modeled this sort of paradigm as giving you sort of uniformly random OTs, but this is not the case. However, if you just instead plug in the endemic security notion, so this existing random OT extension protocol becomes secure without any modifications. But it doesn't quite achieve what people thought it did, is the main takeaway. And if you also use the original protocol where you use allow the sender to choose the base OT messages, you get the identical level of security. And so you basically lose no security by switching to endemic security or endemic base OT. This is the main takeaway there. And then similarly, when we have a corrupt OT extension sender, they can actually do somewhat similar type of attack in that they can bias the messages. I won't quite get into it. They can also do some other weird things, such as choose delta to be 0. And this effectively means the 0 messages equals the 1 messages, which while you might say this is sort of just weird, but in fact, this can lead to attacks on existing, like, for example, private set intersection protocols, which crucially rely on the messages being different. And so again, we don't achieve uniform message security, but instead we can show that you achieve endemic security. And then the final takeaway is like, right, okay, so if random OT extension didn't achieve what we wanted to before, can we make it achieve it? And in fact, we show how to do this. And what you need to do is use our sort of building block where you take your endemic OT and strengthen it to a uniform base OT. And then we also need to randomize the choice bits. And then if you do these two operations, you can show that the messages coming out of the OT extension are in fact uniformly random. And so we don't need to modify OT extension. You just need to change what base OTs you use, and then you're safe. In addition, some of you might have heard like Jonathan Katz and Zhao Wang talk about there's this catastrophic bug in using fixed key AES in various primitives. And we also identified this, and in that this was an implementation bug where people were not following the protocol specification. Instead of they deviated and ended up being sort of a critical bug, which could be easily used to break various things such as garbled circuits. But regardless, we show that if you use our uniform base OTs and uniform choice bits, then you can actually, these insecure implementation bugs actually disappear, and that you can show that you get uniformly random OTs while still using AES or fixed key AES. And the reason you'd want to do this is that it's about 10 times faster than the sort of the original specification, and this is why implementations did it. And similarly, like the other paper I referred to earlier that also identified this as a bug, they provided a different fix which required additional calls to AES, but we showed that no, you don't need these additional calls. You can simply run the protocol as is, as implemented, and it's secure if you use these uniform base OTs. And yeah, so this sort of conclude, we strengthen several existing protocols and show that they achieve endemic security for OT extension. We then show how to strengthen these to our various security notions. Shown here, it's sort of a cool diagram where depending on what base OT you get different properties out of the OT extension. So you can sort of decide what OT extension property you need and then reverse engineer what type of base OT you want. And similarly, we get to around OT extension and identify this bug and some fixes. So yeah, sort of cleaning up OT extension with our new security definition. And yeah, so that concludes my talk. We define this new security notion known as endemic oblivious transfer. Pretty much all oblivious transfer protocols satisfy this definition. We instantiate it from various assumptions, for example, one round requirement or post-quantum, and then we improve OT extension in various ways. And yeah, with that, I'll take questions. Thank you.
Okay, thank you. Thank you for the talk. So we have
Peter, if I may ask, great talk.
Yeah.
First of all, thank you, great work. I wanted to ask, did you look a bit more into the post-quantum security of your construction, in particular with respect to the use of the random oracle?
Yes, that is one sticking point. We did not model in the quantum random oracle model. We're still in the classic random oracle model. And so, yeah, you could potentially run into some sticking points there. Intuitively, we didn't see any, but I also am not qualified to make any strong statements on that.
Okay, fair enough.
So
Just wanted to ask.
yeah, it'd be an interesting exercise to check.
Okay, thanks.
Okay. I have one question about these. So you mentioned just, I guess, one slide ago, these existing OT extension protocols. It didn't become entirely clear to me what the statement was. Are the older protocols not secure, or is it a statement about when you instantiate them with your OTs?
Yeah. So some of the previous works weren't secure in the fact that their functionality was something similar to uniformly random OT extension, but the protocol only actually achieved endemic security. So they were still secure in the sense that like if you're happy with endemic security, then these protocols were secure. But if you needed the strong property, which I think most often you don't, strong property that the messages are in fact uniform, which is what some of the functionalities in those previous works claimed, then you do not achieve this because the adversary can bias the distribution of these random messages. So they're secure, but not quite as secure as maybe claimed.
Right. So the other related question to that is that I had was, so you mentioned that if you have an endemic security, you can go and use that kind of OT in lots of different applications, and it's already enough. So are there any, how can I say, natural applications where endemic security is not enough?
Yeah. Actually, one of these works had one of these. So you might be familiar with this equality check, where you can use Oblivious transfer to check the equality of two values, where one party learns the output. And the way you do this, you would use like 1 out of n OT, and where the person who should learn the output picks the message, that the OT message that corresponds to their value, and then the sender sends over their the message that corresponds to their value. And then if the OT strings are equal, that means the sort of indices that encode the value are equal. While that's fine, right, in endemic security, what it says is that the sender can choose all of the messages. And so the sender could simply make all of the messages equal some constant. And now the equality check always succeeds, always comes out as equal. So even though if the sender might not know what the receiver's choice bit is, they can always convince them that, yes, our two values were in fact equal.
Right.
And this can be used in PSI and ends up not working. So you crucially rely on the fact that the sender messages are all different. And in this case, they're not, because the sender can bias them. But yeah, but I think in most places, you're probably fine with endemic security.
Right. Okay, thanks. I don't see any questions on the Q&A section.
So there's actually one
is
question
one
in the chat.
Yeah.
Okay.
Yeah, so Yashwant Kondi has asked, so regarding the issue with the UC proof, you need to rewind the adversary in the reduction. But is this a problem for UC when you only need the simulation and extraction to be straight line?
So, so extraction, I think it becomes tricky, because if you don't program the other one, you can't really claim that you're extracting the right choice bit, right? It might sort of, the rewinding and the extraction, everything, it's sort of tied together. And that if you don't use the DDH, don't correctly program the DDH challenge, then you can't really claim that they can only use this choice bit.
So
right? You could construct weird protocols
when
where
you're rewinding.
What's that?
Is it actually also in the simulation when you have to rewind?
I think it is.
Yeah. Well, I mean, the simulation rewind It was sort of all the same, right? Like this, yeah, this, you could run the simulator and it would run and it would output something. But if you don't use the reduction in the simulation, then what is your simulator even saying? Yeah, I don't know. It's a weird, rewinding's weird.
No, I think it's you are saying that you will not get a simulation that succeeds unless you actually rewind the adversary in the simulation.
Yeah.
So I mean, never mind into the reason why that's the case. I mean, if that is the case, then there is a problem, right?
Yeah, I mean the simulation will output something, all like the transcript looks correct, but if you don't have a guarantee that the DDH challenge was actually programmed correctly, what is to say that the adversary can't learn both messages?
Right. Sure.
Cool. Can I just ask one more quick question? So I think earlier on in the talk, you mentioned that you had some rumor that this technique might have been used for something else.
Yeah.
Can you say anything more about that?
Oh, well, it's I hear something about Pake and
okay.
1 out of N Oblivious transfer. I don't want to say too much, not my work, but
sure.
Yeah.
Great. Okay, good. So thanks again, Peter. I guess that was it for today. We will reconvene tomorrow for the last day of TPNPC. So see you all back then.